Today we're going to be talking about arithmetic sequences and series in section 4. So in this lesson, we're going to be able to interpret arithmetic sequences and series. So we're going to be able to define these two terms as well as be able to work with them, being able to come up with what we call the explicit definition for these. So the vocab that needs to be known for this lesson includes arithmetic sequence, arithmetic series, the term common difference, explicit definition. We're actually not going to be talking about the recursive definition, so we can kind of ignore that because we want to focus on the explicit. Sequence, series, and sigma notation. Alright, so let's talk about arithmetic sequences first. So what are they? So in general, a sequence is a function whose domain is the natural numbers. So the natural numbers are the numbers from 1, 2, 3, 4, and so on. These are the numbers that you naturally think of when you're thinking of numbers, when you start counting. So you normally start counting 1, 2, 3, and so on. So a sequence is essentially a list of numbers that has a specific pattern that is governed by a function or some kind of rule. So here's an example. So if you're looking at the list of numbers 5, 8, 11, and 14, well, there's some kind of pattern in this sequence, in this list of numbers. If you're looking at 4, 12, 36, 108, there's also another pattern, and see if you can point that out. See if you can actually find it. Alright, so for the first part, the pattern is that you're going to add 3 to each term. So notice if I add 3 to 5, I get 8, 3 to 8, I get 11, and so on. And this pattern is consistent throughout. For the second sequence, we actually have a pattern of multiplying by 3. So if I times it by 3, 4 times 3 is going to give me 12, 12 times 3 is going to give me 36, and so on. Alright, so what we do is we say that A1, or the first term in the sequence, is equal to 5, A2, or the second term in the sequence, is 8, and A3 is 11, and so on. So notice that the domain is represented by the 1, the 2, and the 3, and their whole numbers. So like 1, 2, 3, and so on. And they're positive numbers. For the next part, A1 would be 4, A2 would be 12, and A3 would be 36. So notice that the domain is positive numbers for each of these, and we're referring to the numbers in the subscript, and that represents our domain. So the first example that we have here is actually an arithmetic sequence. It's a very specific type of sequence. The second one is not a sequence that we'll be discussing in this lesson. We'll actually be referring to it in another lesson. So an arithmetic sequence is a sequence with a constant difference between consecutive terms. These are terms that are next to each other. So in this case, the constant difference is actually 3. So this constant difference is known as the common difference, which is, the number 3 in the previous in this example. So part A, we said that to get to the next number, you have to add 3 to get to it. And that's known as the common difference. So that in this case, D, or the common difference, is equal to 3. Alright, so in the problem, they're asking, is the sequence arithmetic? If so, what is the common difference? What is the next term in the sequence? So we got our list of numbers here, and we want to determine if it's arithmetic. So we need to see if there's a common difference. So if we go from 3 to 8, that means we had to add 5, right? Just to see if it's arithmetic. Again, so for arithmetic, you want to see if you add or subtract the same number to get to the next. So in this case, we had to add 5 as well, because 8 plus 5 is 13, and so on. And this pattern consists throughout the entire list. So therefore, our sequence is arithmetic, and it has a common difference of 5. So continuing with the pattern, if we add 5 to 23, we're going to get 28 as our next term in the sequence. So for part B, we want to determine if it's arithmetic as well. So notice to get from 3 to 9, I have to add 6. If I get from 9 to 27, I need to add, I can't add 6 to get to 27. I had to actually add 18 to get to 27. So clearly this is not the pattern in the sequence. So in this case, the pattern is to times it by 3, and so on. 9 times 3 is 27, and 27 times 3 is 81. So this is clearly not arithmetic since we're multiplying by the same number. In arithmetic, we want to add or subtract the same number. So therefore, this is not arithmetic. However, we can still find the next term in the sequence by multiplying by 3. So if we take 243 and times it by 3, we get 729. Alright, go ahead and pause the video and try the following problems first. Alright, so looking at the first part, if we want to see if it's arithmetic, let's see what we need to add or subtract to get to the next number. So in this case, if I subtract 5, that will lead me to the next number. Again, here subtracting 5 will lead me to the next number, and subtracting 5 again will lead me to the next number. So therefore, there's a pattern in adding or subtracting on the same number on both sides. So therefore, there is a common difference. The common difference D is actually negative 5. So therefore, this is actually arithmetic. So the pattern is subtracting 5, so D is negative, and therefore arithmetic. The next term in the sequence is 10 minus 5, or 5. For part B, well, if you look at the pattern, well, if you're adding 2 to get to 4, but however, you're adding 3 to get to 7, and then 5 to get to 12. So this is actually, you're not adding or subtracting the same number to get the next number in the sequence, and therefore it's not arithmetic. Alright, so looking at example 2, given the sequence 3, 5, 7, 9, and so on, what is its explicit definition? Use it to find the 25th term. So what we want to do is we want to know what an explicit definition is. So an explicit definition allows you to find any term in the sequence without knowing the previous term. So it's essentially a nice rule in order to determine any number in the sequence, no matter what. So you need to know a few things in order to find the explicit definition. So here's the explicit definition. So if you want to find any term in the sequence, you have to know the first term. So again, this is actually the first term. This is the common difference, which I'll refer as CD for common difference. And then N is the number that you're trying to find. So the number term that you're actually trying to find. So if you're trying to find the fifth term, then this would be A5, and then this would be N equals 5. Alright, so as we mentioned earlier, A1 is the first term, D is the common difference, and N is the number of the term you're finding. So for this problem, this first term is 3, so A1 has to be 3. So that's A1. Now notice that the pattern is adding 2 to get to the next number. So that's our common difference, which is D. The explicit definition then can be written as 3 plus 2 times n minus 1 using the format for using this formula. So therefore, if you distribute the 2, then you get 2 times n is 2n, 2 times 1 is 2, and then you're going to go ahead and combine like terms. So we got 3 minus 2 is 1. So I get 2n plus 1. And that's my explicit definition. So now if we want to find the 25th term, well, that means that n is 25. So then we're going to plug in 25 into the formula. So plugging in 25 into the formula here, that gives us A25, and then plugging it in here. So we got, actually what we want to do is we can plug it in here, but we can also take this and plug it in to the simplified formula that we found here. So that gives us 2 times 25 plus 1, which is 51. So you can either plug it into either form, and you're going to get the same answer. All right, go ahead and pause the video and try the following problem first. All right, so the first term is 10, and that's going to be A1. So first term is 10, and then notice that the pattern is we're subtracting 4 to get to the next number. So therefore D, the common difference, is negative 4. So now remember that our using our explicit definition, so we're rewriting the explicit definition, AN equals A1 plus D times N minus 1. then now we know what A1 is, we know what D is, and so we can just plug it in. So we have AN equals 10 minus 4 times n minus 1. Then make sure you distribute the negative 4. So we got negative 4n plus 4. Combine your like terms, and that gives you 14. So now if you're looking at the 12th term, well, that means n is equal to 12. So you want to take the 12 and you want to plug it into the formula here. So we got negative 4 times 12 plus 14, which is going to be negative 34. All right, so looking at a word example. So a high school auditorium has 18 seats in the first row and 26 seats in the fifth row. The number of seats in each row forms an arithmetic sequence. So part A, what is the explicit definition for the sequence? Well, keep in mind that this is A1, since that's the first row, and this is A5, since that's the fifth row. So therefore, we know that the sequence is arithmetic since it was explicitly said in the problem, so we can use the formula. However, we need to know what the common difference is. So we don't know how much it's going by to get to the next term because we only know the first and the fifth term. So what we need to do is we need to plug it into the formula for their arithmetic sequence here. But we know that n is equal to 5, so we can plug that in easily. And we know A5 and A1, so we want to plug those in. So if we plug in, we plugged in 5 here. Now we know A5, so A5 is 26 and A1 is 18. And we know that 5 minus 1 is 4, so that's how we get 4D. So we want to solve for D here, so we're going to subtract 18 on both sides. And therefore we get 8 is equal to, so these cancel, and you get 8 is 4D. Then divide by 4 on both sides and you get D is equal to 2. So now that we know D, we can actually plug it in. So plugging in D into the formula as well as A1 gives us the following form. So we know A1 is 18, we know D is now 2, and n minus 1 is just n minus 1. So now distribute. So we get 2n minus 2, combine your like terms, and that'll give you 16. So that's our explicit definition for the problem. So now we want to be able to figure out how many seats are in the 12th row. So 12th row means that n is equal to 12. So we're going to take the 12 and we're going to actually plug it into the formula that we found earlier. So doing that gives us 2 times 12 plus 16, which is going to be 40. So that means that in the 12th row, in the high school auditorium, you have 40 seats. Alright, pause the video and try the following problem first. Alright, so Samantha is training for a race. The distances of her training runs form an arithmetic sequence. She runs 1 mile the first day and 2 miles the 7th day. What is the explicit definition for this sequence? So since she runs 1 mile the first day, we're going to say that that's A1, which is equal to 1. We also know that she runs 2 miles the 7th day, so A7 is equal to 2. So we know that the formula for the arithmetic sequence is this. So we want to plug in the 7th day where n is equal to 7. So we're going to plug that in here. If we do that, we get A7 equals A1 plus D times 7 minus 1. But 7 minus 1 is just 6. So we get A1 plus 6D. Now we know what A7 and A1 are because we just identified them. So we're going to plug those in. So plugging those in gives us with 2 equals 1 plus 6D. So again, the A7 is here, and then the A1 is plugged in there. So now we're going to solve this equation by subtracting a 1 on both sides. So we get 1 is equal to 6D. Then we want to divide by 6 on both sides, so we get D is equal to 1 over 6. Alright, so now that we know D, we can actually plug this into the arithmetic sequence formula. We want to plug it in here. So when we do that, we get A1, which we know it's 1, plus D, which now we know is 1/6 times n minus 1. Make sure you distribute the 1 over 6 over to around the parentheses. So once you do that, you want to make sure you combine like terms here. So 1 minus 1 over 6 is actually going to give us 5 over 6. So there's our form. So how far does she run on day 19? So to do that, we need to plug in 19 into the following formula. So plug in 19 into that formula. So 5 over 6 plus 1 over 6 times 19. Well, this 1 over 6 times 19 is actually going to be 19 over 6. And then since they have the same denominator, we can go ahead and add the numerators to get 24 over 6. 26 divided by 4 is going to be, 26 divided by 6 is going to give us 4 miles. So on day 19, she's going to be able to run 4 miles. All right, so now what we want to do is we want to find the sum of an arithmetic series, or the sum of the sequences. So let's talk about what a series is. So a finite series is the sum of the terms in a finite sequence. So we already identified what sequence is. A sequence is that list of numbers that follows a certain pattern. So if we add the terms in the sequences, that gives us a series. So a finite arithmetic series is the sum of the terms in an arithmetic sequence. So here's an example. Let's say we want to look at the sequence 1, 3, 5, 7. Well, we know that it goes by 2's here. 1 plus 2 is 3, 3 plus 2 is 5. So this is actually an arithmetic sequence. Now, it's called an arithmetic series if we actually sum the numbers in the sequence. So like 1 plus 3 plus 5 plus 7, and so on. So if we add up those numbers, it automatically becomes a series. If you were to just add the first 3 numbers, so let's say you added just 1 plus 3 plus 5, then this would actually be referred to as the third partial sum of the series. If you added the first 4 numbers, this would be the fourth partial sum. So if you were to do the third partial sum, which we call S3, that's going to be the sum of the first 3 terms, which in this case is 9. So to find the sum of any series with many terms, you want to use the following formula here. So basically you need the first term, the last term, the number of terms, and then divided by 2. Alright, so let's look at an example of how to use this. So let's say we have the following arithmetic sequence. And then we want to find the sum of it. So basically we want to find the arithmetic series. So there are 6 terms and we want to add all of them. So n is 6 in this example. Notice that the first term is 2 and the last term is 22. So we know that a1 is equal to 2 and we know that a6 is equal to 22. We call it a6 because that's the 6th term in the sequence. Alright, so now we know n, we know a1 and a6, so we can actually calculate this sum using this formula. So if we do that, we got n is 6. So we plug that in. We know a1 is 2, and we know that a6 is 22. So plugging in this into the formula, we get 72. Alright, go ahead and pause the video and try the following problems first. Alright, so we're looking for a series with 12 terms, and then they tell us the first term and the 12th term, or the last term. Alright, so plugging in this into this formula, we know that n is equal to 12. And we know a1 and a3, so we can simply go ahead and plug it in. So we know n is 12, a1 is 3, a2 is 20, a12 is 25. Plug in the numbers. So notice to get the 6, I did 12 divided by 2, and that's how I got 6. And then I went ahead and multiplied 6 times 28, which is 168. So for part B, this is actually a series. And if you notice, the common difference between each term is actually 6. So therefore, we know that D is equal to 6. We also know that we have 7 terms here. So since we have 7 terms, n is equal to 7. And we also know the first and the last term for this. So all we need is the number of terms, the first and the last term, to be able to calculate this. So plugging it into the formula here, we know that n is 7, a1 is 5, and then the last term is 41. So then plugging this in, I went ahead and added 5 plus 41, which is 46. 46 divided by 2 is actually going to be 23. And then 7 times 23 is 161. And that's all there is to it. Now we're going to talk about sigma notation and how we use it. So sigma notation is actually used for series. So the sum of n terms of a sequence can be written using this sigma notation. So this right here, this big letter here is actually the Greek letter sigma. So this is the Greek letter, and it's actually capital sigma. So there's a lowercase sigma and an uppercase sigma. So this is uppercase sigma. And it just stands for sum. Now the bottom term is actually called the index. And index I counts through the terms in the partial sum. So this is saying, go start with the first term and then make your way to the last term. In the notation, it takes the values from 1 up to n, where n is a number. So you can use the explicit formula that we talked about earlier for an in order to plug this in for ai. So for example, let's say that an is 1 plus 2n from one of our previous examples. Let's say that was our explicit. Then you can take that and you can plug it in place of ai here. So what we do is we plug it in place of ai, and that's what we get there. And we know that, let's say we want to sum the first 5 terms, so then n is 5. So we plug that in up top here, that's 5. So this is saying to start at I equals 1, so plug in 1 first, and then plug in 2, and then plug in 3, all the way up to 5. So plug in I equals 1, 2, 3, all the way up to 5, and then add the results. So if we do that, we're going to plug in 1 first, so we plug in I equals 1, and then I equals 2, then 3, then 4, and then 5. And then once we do that, we add up all of the results together. So doing that, so actually doing that gives us, we know that this is 3, that's 5, 7, 9, and 11. So notice that 3, 5, 7, and 9 is just the actual terms in an arithmetic sequence, and we're just adding those together. When adding those together gives us 35. So let's look at another example. So let's say they ask you, what is the sum from 1 to 9 of 2i minus 6? So again, the sigma just means sum, right? So this means sum. This means add up all the terms. So find the sum by writing out the terms in the series. So in this example, we know that ai is this guy, and it's 2i minus 6. So in this case, we want to find a1, the first term, by plugging in 1 in for I. So 2 times 1 minus 6, which is negative 4. Now we want to find the next term, which is 2 times 2 minus 6. Then the next term, 2 times 3 minus 6, and so on. So repeating this process gives us all 9 terms of the sequence. And we want to find 9 terms because the sum is from 1 to 9. So now that we know what those 9 terms are, we can go ahead and add those together. So add all of these terms together. So notice we have the negative 4, the negative 2, and so on. And that gives us 36. All right, looking at part B, we were given the series. So we're given all the terms, and we just want to add them up to find the series. We want to convert this to sigma notation, and then we want to find the sum. So notice that a1 is equal to 2. And we know that the common difference is 7 because the terms are going by 7s to get to the next guy. And then we know that the last term, an, is actually 7, or 79. So what we need to do is we need to find the number of terms. This doesn't actually tell us how many terms we have. It just gives us a dot, dot, dot. So in order to find that, we need to use the formula for the arithmetic sequence. So now we know what an, a1, and d are. We need to figure out what n is. So plugging it in, we know that an is 79, a1 is 2, and d is 7. So go ahead and distribute the 7 here. We get 7n minus 7. Combine your like terms, so 2 minus 7 is negative 5. Alright, so now we know that 79 is equal to 7n minus 5. So we can solve this equation for n. So add 5 to both sides. So you get 84 is equal to 7n. Now we want to divide by 7 on both sides, and so n is equal to 12. So now we know that there are 12 terms in the sequence, or in the series as well. So we want to go ahead and plug that, make use of this number. So remember that an is 7n minus 5. So that's this guy that we just found. So that was our an. So we're going to use that to our advantage. So in order to write this in sigma notation, we need the sigma, the capital sigma. We know that we always start from 1 here, and then there are 12 terms. This is where the n comes into play. So we know from the n that there are 12 terms. And now we also know that this is an, so we can replace the n with an I and plug it inside. And that's our sigma notation. So now in order to find the sum, we need to use this formula. So we know that n is 12, so we're going to go ahead and plug in 12 here. And we know that a1 is 2. And we know that, so this is a1, what we found earlier, and this right here is a12. So then plugging those into the formula and plugging and chugging, we get 6 times 81, which is 486. So you can imagine using this formula is actually quite helpful. Instead of adding all the numbers from 2 to 79, you can simply use this formula and then get the answer right away. Alright, so go ahead and pause the video and try the following 2 problems first. Alright, so we want to find the sum of the series. So we want to find the sum from I equals 1 to 13 of 3i plus 2. So if we want to find the sum, well, we know that there are now 13 terms that we want to find, so that's our n. So what we want to do is we want to figure out what our a1 is, we want to figure out what our a2 is, all that stuff. So in order to figure out what the first term is, all you're going to do is plug in I equals 1. So you're going to plug in I equals 1 there, and then you're going to plug in 2 and so on. So if I plug in 1, I get 3 times 1 plus 2 is 5. Now go ahead and plug in 2 to find the second term. 3 times 2 plus 2 is 8. Plug in 3 and you get 11. If you plug in 4, you get 14. So notice that there's a pattern to this. So go ahead and repeat for the next few terms. So you want to repeat it all the way up to n. N is equal to 13. So actually there should be a 13 here, which would be given by 3 times 13 plus 2. Alright, so I went ahead and made the adjustments, and now we have 813 in the problem. So now we know 813 is actually equal to 41. So now we got all 13 terms. So remember that we wanted all 13 terms because we wanted to sum the terms from 1 to 13. So now we got all the 13 terms. We can go ahead and add them up together. So we got 5 for the first term, 8 for the second term, 11, and so on. Adding those numbers gives us 299. Alright, so now we have the following series, 8 plus 13 plus 18, and so on. And we want to convert that using sigma notation. So in order to do that, we need to figure out how many terms we have. So we know that a1 is equal to 8, which is the first term. We know that the last term is 43. We know that it goes by 5s because 8 plus 5 is 13, and 13 plus 18 plus 5 is 18, and so on. So we know that that pattern repeats. However, we don't know how many terms we actually have here. So in order to do that, we need to use the following formula. So this is the formula for the arithmetic sequence. So plugging in 8 and oops, so it's actually so plugging in 43 and then plugging in 8 and for A1, plugging in 5 for D, gives us the following. So we got 43 equals 8 plus 5 times n minus 1. So we want to distribute the 5, and we get 5n minus 5. Combine your like terms. So 8 minus 5 is going to be 3. So now we know that 43 is equal to 5n plus 3. So we can solve for n. So subtract 3 on both sides. So now we got 40 is equal to 5n. So we want to divide by 5 on both sides, and we get n is equal to 8. So now we know there are 8 terms in the series here, in the sequence. So keep in mind that we know that an is 5n plus 3 because we just found that right here. All right, so since we know that, we can write it in sigma notation. So we know that n is equal to 8 because we have 8 terms now. We always start from 1, and now we know that an is equal to 5n plus 3. So this should actually say I. So cross that out. This should actually say 5i plus 3. All right, so we went ahead and made the adjustments. So now this is now 5i plus 3 instead of 5n plus 3. All right, so now if we want to find the sum from 1 to 8 of this guy, we need to use the following formula. So this is the formula for the series. So if we want to find the sum, we know that n is 8, so we can plug that in. We also know that a1 is 8, and we know that an is 43. So we can plug those in. So we know that 8 divided by 2 is actually 4, and then 8 plus 43 is 51. Multiplying those together gives us 204. So now what we want to do is actually apply series to an actual scenario. So in the scenario, we have a pyramid of cans that is on display in a supermarket. The top row has 1 can, the second row has 2 cans, and the third row has 3. Suppose that there are 10 rows of cans. How many total cans were used to make the pyramid? So notice in this case, they're not asking for how many cans there are in the 10th row. They're actually asking for the entire total for all the rows. So if you were to add them all together. So this is a problem of series, not sequences. So we can write the number of cans based on the row as an arithmetic series. Or a sequence rather, sorry. So this should actually say sequence. So we'll just shorten that to SEQ. So the common difference is actually 1 because the top row has 1 and then the second row has 2 and then the third row has 3. So you're just adding 1 to get to the next row. We know that the total number of rows is n is equal to 10. So a1 is equal to 1 and a10 we need to actually find. We actually don't know what a10 is based on the problem. However, we know from common sense that if we were to add 1 to every single row to the previous row, we know that we'll get 10 cans. However, just for the purposes of showing you the math, I'm going to actually take you through the math. So using the following formula for the sequence, we want to find a10. So we're going to plug in 1 for a1 because we know that this is a1. We know that the common difference is 1, and then we know that the number of rows that we're looking for is 10. So therefore we get 10 cans, which makes sense from common logic. So now using the formula for the series, we actually can plug in the numbers what we know. So we know that a10 is actually 10, we know that a1 is 1, and we know that the number of terms n is actually 10. So therefore we can plug it in. 10 divided by 2 is going to give us 5, and then 1 plus 10 is 11. 5 times 11 is 55 cans. So there are 55 cans in total. So if you were to have, let's say this is your first can for the first row, then you have the second row, then the third row, dot, dot, dot. If you were to repeat this and add up all of the cans, you would get 55 cans. All right, so to summarize the lesson, you have an arithmetic sequence that we discussed, and we have arithmetic series. So note that in arithmetic sequence, each term is equal to the previous term plus a constant d, which we call the common difference. So for example, if you had 3, 5, 7, and so on, the common difference in this case is 2, and therefore this is an arithmetic sequence. So the formula for an arithmetic sequence is given here, and we call that the explicit formula or the explicit form. And then the formula for an arithmetic series is this. So a series is when you add the terms in the sequence. So in this case, if you added 3 plus 5 plus 7, that would give you an arithmetic series or a partial sum. Now the symbol for an arithmetic series can be used with sigma notation. So that's this guy right here. So that's our sigma notation. Remember that the Greek letter capital sigma actually stands for sum. All right, so in the next lesson, we're going to be discussing how to solve equations and inequalities.